Good day to everyone and welcome to today's weather briefing. I'm Petra Mikuš Jurković from Croatian Met Service, working as a forecaster but also as research assistant. So that here on the photo you can see the building of the Croatian Met Service where we are working. And now first I want to ask you, where are you from? So please, if you can use markers or arrows and mark the place where are you working. Okay, so we have the people from all around the Europe. And if somebody is outside of the Europe, he can click on this here box, but we don't have anyone. Okay. Thank you very much. So I am from Zagreb, that is capital city of Croatia. So Marko also marked the Zagreb. Okay, now we can move on a briefly analysis of today's situation. Here we have the air mass RGB, and we can see that a largest part of Europe is under the influence of high pressure. So very large anticyclone, and these cyclones and fronts are situated far on the north. As you can see, we have here the 3 cyclones, and this is the 4th one. These are very deep and well-pronounced cyclones. And also on this air mass RGB, we can see this dry intrusion of stratospheric air, and also here the jets in these brownish reddish colors. So these cyclones affect the weather in the northern countries of the Europe, where will be here maybe cloudy with some rain. But as I say, in the largest part of the Europe, we will have stable weather condition, which will persist surely for 7 days in this part of the central and the southern Europe. And in this region, even the ridge will get stronger, so we will have so-called omega blocking pattern. And during the autumn, in that kind of weather situation, one of the biggest problem is fog. So their evolution and also time of dissipation. So how long will it last? We can have also a long-lasting fog, even a fog during the whole day, but have a strongly influence on maximum daily temperature. So in that area where we have a long-lasting fog, the temperature is lower. And if we move on, so here we have also the air mass RGB. And now I have one question. You see here over the Mediterranean and Western Europe, these greenish colors, which indicate the warm air mass. But please look at this region here, and can you find some interesting features or feature here over the sea? So something different in that warm air mass, just in this region. Yes, that's very good. So here, where you marked, here you can see that blue color, which indicate something colder than the surrounding air mass. If you go further, so if you look at the model temperature, so the ECMWF model temperature at 300 hectopascals, here at the place of this blue color, you can see, if I can say, lake of the cold air. So it is the rest of the trough, which moved further to the east of the continent. And also, if we move back, just to clear pointers and annotation, if we move back, also I want to mention that here on the edge of the satellite image, you can see just small part of the hurricane Ophelia, which moves over the Atlantic. And if we look on the polar satellite here, on the Terra Modis polar satellite, Here you can very nicely see this rapidly rotating storm system, so this tropical cyclone, actually hurricane. Also you can see here the eye wall around and the surrounding rain bands. And this tropical cyclone usually produces strong winds and heavy rain. Now, if we look at the NOAA forecast charts for this tropical cyclone Ophelia, here you can see on Sunday that actually at the end of the week, so on Sunday, it will pass very close to the coast of Spain and Portugal. And on Monday, as a tropical storm then, because here is hurricane and here is the tropical storm, hit the British Isles. So in that areas, we can expect, as you can see here, we can expect some severe or tropical force winds. Actually, it will be very interesting to monitor the evolution and the intensity, as well as the path of this tropical cyclone in the next few days. But now, as I mentioned before, in the stable situation, which will persist surely for 7 days here in the most of the Europe, the biggest challenge in the forecast is fog. And now I want to show you yesterday's situation with long-lasting fog in the Croatian inland. So somewhere here. We have a high pressure system over the Croatia and the neighboring country, also over the part of the Central and Western Europe. And I want to mention that the day before, during the morning, here in Croatia, we have some rain in the inland, and so we have the humid land and a stable situation without winds. What is favorable conditions for long-lasting fog. And if we move further, now we have here the pseudo soundings from Aladdin model. So now please look at this pseudo sounding for the yesterday night. So here we have a yesterday night, morning, and a forenoon, and the full red line is temperature, and dashed line dew point temperature. And here also you can see the wind barbs. So this black line here represents the data from real sounding at 00 UTC in Zagreb. And now I have one actually exercise for you. So please can you just use these data, so these pseudo soundings? I know that you need some more data, but try just use these data, forecast the approximately start time of the fog in Zagreb, and also the time when it will dissipate. So maybe you can actually type your forecast in the text chat. So you have look here for the temperature inversion and in the lowest layer, so in the surface temperature inversion, but also check here on the wind barbs for the information about the wind speed. So I can wait a minute if we have some. Yes, we have some forecast in the text chat. Okay, it starts at about 9. Fog from, okay. Yes, that is very good. This forecast from Max. Okay, I can say that the forecast is very, very good. So here on this, you can see that we have the temperature, actually, this surface temperature inversion. Very nice. So the fog can start to develop something around 21 UTC. And during the night, as you can see, we have a nice temperature inversion. Also, the wind was very weak. Actually, it was calm. And here, something here in the forenoon, so the inversion is weaker. So we can say that somewhere between 10 and 12 UTC we can expect the fog dissipation. So you gave a very good forecast. And now we can look at the 24 hours microphysics RGB to see what happened. So here is the fog and low clouds, represent with light greenish or yellowish color. And here at 21 UTC, you can see that the fog starts to develop in the Croatian inland. Also, it become thicker here around the sunrise and dissipate. So Zagreb is somewhere here and dissipate in Zagreb at about 11 UTC, but also in the rest of the inland. So this fog here dissipate in the next half hour. And we have actually sunny afternoon in the whole Croatia. And just I want to mention that this fog was actually radiation fog. So here, you know that we have the rain the day before, so I mentioned it on the previous slide. So the land was humid, and if we look at this vertical cross section of relative humidity, we can see that we have a high humidity values just at the surface. While if you look at this scheme, in the case of advection fog, this stable and I can say the maximum of moisture air is a bit higher above the surface. And I want also to show that because the fog appear usually during the night in autumn and also winter, for the monitoring of their evolution during the night, we can use 24 hours microphysical RGB or night microphysical RGB right here. But during the night, this night microphysical RGB provides better color contrast, you can see here, between fog and cloud-free surface. And also these two RGBs are much better than just single infrared 10.8 satellite channel for monitoring fog. But during the day, for the fog detection, it is good to use some of the HRV RGB products, like this here, so HRV fog, near natural, or maybe clouds RGB. On this, for example, fog RGB, fog is in the shades of pink, while on the other two, so these near natural and HRV clouds RGB, it is in some yellow or yellowish color. Also, for example, on fog RGB, you can very nice distinguish snow cover from fog. So snow in this RGB are in cyan color, so it is much easier to distinguish the fog than just looking at single HRV channel. So now, from the actually, I want to show something completely different from the stable foggy situation. We will move to the extreme precipitation. I want to show you one case in September, because in September in Croatia we have extreme precipitation events. Here on these photos you can see some floods and flash floods which happened during the September in Croatia. So here you can see the monthly precipitation anomalies for the September for Croatia, and almost all Croatia, as you can see, is in green color, but is actually wet. So while this western part, so these and these, was even extremely wet. And in these extremely wet regions, on the four weather stations, we have measured precipitation amount records. So the largest precipitation amount measured in 24 hours in the history of measurements. On this graph here, you can see monthly precipitation amount for these four stations. And for September, if you look right here, it is quite extreme because this red line represents average, so calculated for 30 years period. So you can see that we have a really extreme amount of precipitation during this last September. Now, one extreme precipitation actually event occurred on 11th of September. What is very interesting that on that day was last weather briefing, and they mentioned that severe convection can occur in this central, I can say central part of the Mediterranean and also here in the Adriatic Sea. And now we can check what is happened. So on this ERMAS RGB, you can very nice see this dry intrusion of stratospheric air here in the, I can say in the central Mediterranean, and also you can see here the convective clouds east of this PV. In the upper layer at 500 hectopascals, we can see this very nice low, so in the upper layer, and also this low have this colder air, so the temperature is actually shaded. And if we move further, here in the pink color, if I can say, is the intrusion of stratospheric air, so we can check for the PV. And in this upper level low, cut-off low, we have this dry intrusion of stratospheric air, what can enhance the convection. And these yellow lines represent jet stream, which is situated here around this upper level low. And here at the front side of this low, we can see convection cloud on infrared 10.8 satellite images. So now we will look in vertical cross-section right here, just in this region of PV anomaly, and here where we have the convection. And here are the cross-sections of potential vorticity. So these two PV units, which is associated with thermal tropopause, is somewhere between, I can say, 600 and 700 hectopascals, so quite low. And if we look here, so eastern of this intrusion, right here, we can see a very strong upward motion, so we have the negative omega values. Now I have one question for you. So can you please, on this here vertical cross section, indicate where do you expect positive, or if you want, cyclonic vorticity advection? Just marked with a marker or arrow, whatever you want. So on this vertical cross section, okay, we have one answer. Okay, that's very good. Yes, here, so at the, I can say, leading edge of the PV anomaly, so at this dry intrusion. And we can check now on the next slide. Yes, that's very good answers. So that is the ERMAS RGB and convective vorticity advection, and we can see that we have the positive vorticity advection here actually when convection is developing, so here at the front of this PV anomaly, so the dry intrusion of stratospheric air. Also, I want to show you here that at the day, if you look at the wind in the lower troposphere, so at 700 hectopascal, we have this, I can say, southern but also southwestern flow, which bring moist and warmer air from the sea, and very strong convection during the night develops somewhere, I can say, here in the Adriatic. So you can see here. And if we look at the wind at the ground, so on this image here, in the Adriatic, so in that region where the convection developed, we can notice the convergence line between southeastern wind and also here the southwestern wind. So we have the convergent line in this area. Also, if we move on to the Cape values of ECMWF model, you see that we have a very large Cape values in this region where the convection developed. So all previous mentioned parameters were actually suitable for organized convection development. And now I want to show you on this animation. So please click yes if you can see the animation. Okay. I can wait. Okay. Okay, do you all now see the animation? Please click on yes button. Okay, so if you see the animation, we can see what happened. This is enhanced infrared satellite image. So actually, we have a very strong convective cloud that you see in the Italy, and also the MCS starts to develop in the Adriatic, and it was pretty stationary. So we have extreme precipitation in the northern part of Dalmatia, I can say, also where the most intense part of the storm was. So there was the storm with the coldest cloud top temperature, as you see. So it was quite impressive mesoscale convective system. Okay, now we can move on. And now we can look at the sandwich product, which is one of the best for monitoring strong convection and convective cloud tops, because it provides information about the 3D structure of the cloud tops, but also about the temperature of the cloud tops. So you can see here this very nice MCS and very nice oval shape, and also I can show you that here is an overshooting top, which also represents a very strong updraft. And this is the strongest and the most intense part of the storm was actually on the northern part of Dalmatia in Croatia. And now, if we move on, other products which is very good for estimating, I can say, intensity of storm is severe storm RGB or convective storm RGB. And here the yellowish color represents strong and severe updraft, and I can say most intense part of the storm. So this yellowish color came from very small ice particles, but also very cold cloud tops. So these small ice particles is at the top of severe storm, while if I can say, have normal convective clouds with moderate updraft, then we have a larger particles at their tops. And right here, you can see this yellowish color, which represents most intense part of the storm. He's situated near the town Zadar, where we have extreme precipitation, and also in Zadar we have floods and flash floods all over the city. Now we can look what happened in Zadar that day. So if you look here in 24 hours, more than 200 millimeter of rain fell most in just 2 hours, if you look here in the morning. And on this photo, you can see it caused flash floods all over the city. There were a lot of damages on roads, as you can see on this photo here, but also on houses and buildings and and agricultural land outside of the city. You can maybe see here, I have one video with a flash flood, so please click yes if you can see the animation or video, so that you can see how extreme that was. So the roads were completely flooded and lots of water in the parks and squares. Also you can see also I want to say that the hospital in the city was, so that was a very big problem. Also schools were closed, so really extreme and severe weather conditions. I hope that you all can see the video. I see that most of you can see it because you click yes. Okay, so that's actually all from me today, and I want to finish with this very nice photo. So taken yesterday from our window in office. After the foggy morning, we have a pretty nice and sunny afternoon. So thank you all for your attention.